Alright, another DraftScience video presentation. Okay, we're staying with this two slit stuff, I guess, for a little while longer. Even though I think it's been done. Been there, done that. Alright, so on this video, DraftScience versus QM versus solid mechanics. Just so if you want to go read the whole comment, that's where it is. So this Mesokosmos guy has done a ton of research, obviously. Blah, 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 blah. Lots of papers, blah, blah. I hate to diminish all these other people's work, but I mean, frankly, the problem is that they always, instead of just pointing out where the conventional model is substantially broken, they have to always add their crap. And so their crap ends up just ruining the paper, frankly, because their explanations don't work in all the other ways. They break so much else that they're not fixing anything. Their model is still so inconsistent with what photons do in all the other circumstances. The idea is to come up with a model that explains everything, frankly. Okay, all of physics. It fits with everything. It fits with gravity. It fits, with some sort of model of magnetism and everything. And their models don't, frankly. So, like I said, you could write a paper about all the ways their model doesn't fit, just as they're writing a paper about how the conventional model doesn't fit. So anyway, it's kind of circular. So we will read somewhere down in here. Okay, maybe here. Okay, looks like these guys emphasize the influence of the edges. Okay, so the surfaces are where the action happens. The fringes are being created by photons that travel near the surface. The ones that don't travel near the surface do not become fringe photons. So it's not a Feynman kind of universe. Stuff doesn't go in anywhere and go to Pluto. I mean, it doesn't. There is a physical mechanism. The variable, it is a hidden variable, and it's not very hidden. Okay, it's right there in front of you, the surface. Anyway, but as said, their underlying model is totally different, right? So that's the big problem. Is they're still creating photons that have properties. They're still making photons complex objects rather than simpler objects. That is something I was thinking about early in our correspondence. I need to take this cake in 3 parts: the correct setup, the geometry, the explanation, the model. Okay, so again, it's just unfortunate that we can't draw. We don't have some magic drawing board that can actually do, real proportions. We can't do that. So you have to use your imagination a little bit to fix the flaws in what we draw. But I mean, that would be the way to do it, right? Is to make a little model of the big thing, one that you can fit on your desk. You want to understand how the car works. It'd be nice to have a little model that you could take apart on your desk. Alright, anyway, I'm sure there are a few, and eventually will be many models explaining why slit edges, 4 surfaces, and scatter in there would be the right way to explain fringes. So I hope that doesn't happen, frankly, because there's only one right answer. So again, all of these bad guesses, frankly, are, in my opinion, noise. Okay, and they just distract people from getting the right answer, because I think the right answer is already convincingly argued, that photons just have to be thought of as simple forms of energy. They move the speed of force, not the speed of light. Okay, that they're just a kind of force, and the kind that makes them significant is the fact that their quanta of force, the elemental force of a photon, is in little bits that are at a frequency. That model works, in my opinion, really well. Maybe you have even influenced these German and Chinese guys with your 4 surface edge scatter idea. Who knows? Indeed, I'm interested in studying your 2+2 model too, but as I said, I like to get the basic setup right for the double slit experiment. So I think the basic setup is based on, is understanding just the simple parts. If we could agree on a simple fact, I'm saying that fact just kind of if you take it to its conclusion, it answers all these questions. I mean, it kind of just finishes the conversation, because you just say, well, what's the consequence of that? And what's the consequence of that? And what's the consequence of that? And it just, it finishes it. You don't have to do all this. I have to fix this stupid chalk dispenser. Okay, well, that'll be close enough, I think, to working. Alright, so slit. As discussed, you can view the slit, alright, as being just a distance between two sources. The distance would be in increments, okay, of the wavelength of the light you're putting in. And by understanding it that way, you can understand that what it's going to project is essentially an image of this out to the world. And that image is going to have these wavelength differences, in these two distances is just going to be reflected on this surface. So you're just saying, well, first let's figure out what the surface should look like. I'm obviously saying an infinite plane is not a rational surface, because there are no such things, right? So we know that's not a very good surface to view something on, because it has all kinds of automatic retardations in it. It has an infinity in it, which is just too useless. Alright, so anyway, and all I'm asking you to accept as a fact, if we can accept this as a fact, that what's going to happen here is there's going to be places you could pick, okay, and we'll just say they're on this line, okay, not for any reason, we just decide to pick this line as a place to look. And the idea is that this image is going to project to this surface, and it's going to project, okay, rather accurately, in the sense that the places where you can possibly have the difference between this path and this path, not this path and an L, okay, you're not comparing this and saying, is there a wavelength of difference? You're comparing this and this. So this line got shorter, you can see. This line got longer. So as this one gets shorter, this one's getting longer. And as you're going around. But I'm just saying, if you could accept the fact that whatever number is in here is going to be here. So if this is 15, this is 15. Alright? And so that kind of just, who cares whether this one is, 1/10,000,000th of a millimeter, a little bit bigger than this one. I mean, I'm not saying it's unimportant. I'm just saying, for the sake of understanding, let's just recognize that whether these get progressively, like these are small, the distance between them is smaller here, and then they get further and further apart, or not. I'm saying clearly it's debatable what line we're putting this on. Are we putting it on this circle? See, I could make another circle. I could make a circle from this line, okay, as the center. And that circle would be here. See, a new chalk failure, right? And if I went from this point, that circle would be here. Now, these are hugely exaggerated because I'm doing this on a chalkboard at the wrong dimensions. So this difference is huge, but it's not going to be huge at the proportions that the actual experiment happens at, which is, these wavelengths are, much less than a millimeter, and this length, this distance, is much more than a meter. So it's not just 1,000 to 1, it's many thousands to 1. So the difference in these arcs, okay, is going to become irrelevant at that huge distance. At that huge distance, this little tiny distance isn't going to mean anything. It's not going to be visible. You're not going to see it anymore. So I'm just saying, I don't think you should get hanged on this. Now, the fact that your mathematics has a very dramatic, because you're doing some kind of, I don't know what you're doing exactly, you're doing some kind of geometry to figure out this point. But that's the key problem, is you have to figure these points as being, that's why I use the string analogy, because you're not comparing it to some L number. You're comparing it from this path length to this path length. And obviously as this one gets longer, this one gets shorter, and vice versa on the other side. And that's the real, you have to be careful to be making your comparison not to an average length, but to the actual length, to find out exactly where there's a on. Alright, but that should explain my perspective well enough. I'm just saying, once you concede it's the same number of wavelengths, why would we nitpick about whether, you know, the nodes are this big or this big? Yeah, you're not gonna. It's not gonna be enough of a difference to matter. Let's see. I know you have explained the geometry of the pattern and the force-bit composition of the photon many times, but there are many subtle parts and questions related to them. But the point is there's nothing subtle about how wrong the conventional argument is, and that's sort of what's annoying about what you're doing. You're holding me to a scrutiny that you're not even close to holding conventional physics to. I mean, the video, that Dr. Lincoln made is a Dr. Quantum video. It's full of misinformation. It's a pile of shit. The patterns aren't shown the way they actually are. He doesn't go into any of the geometry. He doesn't, I mean, it's vacuous, childish mush by comparison to the amount of detail you're attempting to extract from every other theory. And that seems a little bit unfair when you first should be very clear that you are, that as much as I can't give you every single bit of a perfect explanation, I think it's pretty perfect, but whatever, they've given you nothing in terms of any solid foundation. There's almost zero valuable content in his video. And that's what you should be stating as a premise first, is that their theory is worse than any of these competing theories. It's much worse because it's so inaccurate. At least these other people attempting to describe the phenomenon understand that it's clear that you can't make two patterns out of two waves. Two waves aren't going to make the double slit pattern, so you're stuck with the fact that you've got to come up with a four-source explanation. And the four-source explanation is so obvious. If there's two sources in a single slit, well, then there's four sources in a double slit. It's almost just too obvious. It shouldn't even have to be argued to reasonable people that you can't start with the premise that the two-slit experiment is about two waves, because it's obviously not about two waves. And that should be emphasized. I mean, all of this, it just smells a little bit like, wow, this is kind of silly, right? We know the conventional theory is horrible, and that should be taken down before we attempt to replace it. It's just, we're having two conversations, right? We're having a conversation of why what I'm saying is right, and a conversation about why what they're saying is wrong. And you're saying the one we should emphasize is this one, mine. We should, verdier it to pieces, and we shouldn't do any examination of theirs. Anyway, when photons break and force bits scatter from the edges, the surfaces. So let's understand that's the same process, right? They don't break and then scatter. They are scattered, which breaks them, okay? They're not going to be necessarily, they're not going to land with the same pattern they had when they left, because they're going to different locations. And so the keys might not fit anymore. By which mechanism do they know to orientate themselves towards the screen? Okay, so now I have explained this, but I'll do it again quickly-ish, maybe. Sort of, maybe. Yeah, maybe. Oh dear, it's a little wet. Alright, well, too bad. I'll take a little pause then. Good for me, probably good for you too. I don't know, we'll have to see. Yeah, because you don't get much out of the pause, do you? You don't get to relax and, blah, blah, blah. But anyway, too bad. I'll be back. Almost instantaneously. Alright, I guess I could visualize some of this or make it understandable without the necessity of using that right away. So anyway, so as I've explained, so thinking of light as a force, it is completely understandable that you have a conduit or a catalyst when the force has to interact with a force. That is, you move an electron. And when you move the electron, it changes the force field, okay, somewhere else. So the simple idea is that there's an electron sitting somewhere, and I hit it. Okay, let's say I hit it from behind. That's a better visualization, right? Okay, so the electron's here. I hit it from behind. The electron moves. When it moves, it did just what it's doing to the screen. It's changing the force here, okay? And by doing that, it's taking this force, the photon that I hit the electron with, the piece of a photon I hit the electron with, is now being converted into a new force that will reflect to the world. All right, and likewise, when the electron went this way, that's the same as the electron going this way from the other viewpoint. So in a sense, I've made the positive portion of the photon in one direction, the peak of the wave, and I've made the nothing, the empty, the low part, the vacuum, when it moved back the other way. So I'm creating two photons when I'm interacting. When the force is interacting with an electron, it's always interacting in the sense that it's creating two universes, the forward one and the reverse one. All right. So with that understanding, okay, you're really saying, okay, here's a surface. So pretend this part's that way, solid, and you're going this way. The point is the electrons are oriented to the surface. So if they're just doing this, they move away from the surface, they move towards the surface. They move away from the surface, they move towards the surface. The idea is when the force bit's going to interact with the electron isn't stationary, it has momentum. So now the electron isn't going to just move forward and replace the photon with a new photon. You could sort of understand, right? If it just moves forward, it's just taking my force, right? I had a force. Just imagine this is a force, but it's really invisible. The force was doing this. You can't see it. But when it hits the electron, you can see the electron. So the electron is the thing that moves forward and replaces the force with another force. But it's always it's in the same direction, right? Well, these electrons are moving in and out of the material. So when you hit them, they have momentum. And they have momentum either going that way or they have momentum going that way. So you're really just saying, I'm going to hit the electrons, where does it go? Well, it's going to go that way, right? Because the electron's going to move that way or it's going to move that way, right? It's going to push in those directions into the universe. And when it pushes, it's going to do this. It's going to reflect force. And when it reflects the force, that's what's going to hit the target, the new reflected force. The force that was actually coming the other way, it's now going to go back that way, but it's going to go back at a different time than it would have if the electron didn't move. But the point is the orientation will be this way and this way. That's which way the electron will move. It won't go this way, or that way, because it's not moving in those directions. It's going to go this way or that way. So it's going to curl around the surface, or it's going to be pushed away from the surface. So that's why the slit experiment illustrates so well the fringes, because clearly the fringes are only in one plane, and they're only in one dimension or one plane, because that's how the electrons are moving, in that plane. Yeah, there, I did it without the blackboard. I think I did it. I believe I did do it. Okay. All right. How do they orient towards the screen? You said it's not random, but 50-50. Okay, so the other point is now what's going to hit the screen? And this is where it gets a little more complicated because, yeah, you have to account for polarization also. So they're going to be polarized after the event in a sense that the photons aren't going to be able to be reconstructed in this plane as easily as they're going to be reconstructed in this plane. So it's sort of like a rainbow polarizes light. The same kind of effect is happening. You're going to polarize the light that arrives on the surface. Is going to tend to be in this plane. Okay, the photons are going to tend to land ... in that plane, and not up and down, because the up and down, you're not going to have a very hard time restoring that as you move the electrons to different locations. But I don't want to make this too complicated. All right, so the fact that I'm arguing is that photons land on a surface. It's not just that they hit, okay, one tiny electron, one piece of the surface, and that the electron goes in, it hits an electron, and then it hits the same electron, then it hits the same electron. That's not happening. The photon is hitting a surface that is a crystal, okay, of atoms. It's domains. It's a matrix. It's a geometric configuration, and what it's going to do is it's going to hit elements of that geometry with the pattern, which means that I could argue that the first electron hits, and the other atoms are all pressurized. So yes, it affects the atom it hits, but it also affects all the connected atoms. So all the connected atoms feel the pressure. When the electron goes in, it causes all of these atoms to, you could argue, expand just a tiny, tiny bit. Their electrons get pushed out a tiny, tiny little bit. And so you could argue that there was a pressure, okay, here, a pressure line that's moving with the atoms. And so what's going to happen is you hit here, and then you're going to hit again, okay, some distance from there, so right here. And now you're going to cause a new bullseye right there. So you have a little bullseye here and a pressure wave moving out. Then you're going to hit it again with your second photon, and that's going to create more pressure. And so now you've increased the speed at which that pressure wave is moving, but you gave it more pressure. You pushed harder on the electrons that are expanding on those atoms. So as those atoms expand, you're adding velocity to the expansion. And then you hit it with another new bullseye here. And the fact is, if you do that 3 times or whatever, you have a photon. You have now enough energy to kick the electron out of the atom and create an ion. And by kicking it out of the atom, you've essentially created charge on the edge of the atomic domain. So now the domain, let's say this was a domain of atoms, a configuration of atoms, and you pop an electron out of the domain. Well, now it's in this section between the crystals, and the section between the crystals, is a high pressure, and so now electrons move really fast, okay, to balance the pressure between these atoms, because these atoms want to be connected to each other, but they can't be because there's a constant agitation of extra electrons that keep getting in the way, so it has to pump them out. And that's what's electricity, is the pumping of the... So I can give you this more detailed explanation, but frankly you're not demanding it from conventional physics. You don't require them to explain any of it. You just take for granted. You say, well, electron jiggles, and it has a magnetic moment thingy, and electricity is made. You don't ask them to explain anything. But anyway. So it's something, I'm saying it's something like this. Okay, a photon doesn't hit an infinitesimally small space. It hits a rather large area of atoms. It hits a place that has maybe 1,000 atoms in it. Okay, you can't make a photon. You can't reflect one off something tinier than 1,000 atoms, let's say. Something smaller than that, you can't see that actual object with a photon. That's why optical microscopes fail at a certain point, because you're getting nothing but scatter back. You can't get the whole photon to hit a whole atomic surface and create a whole reflection. So you can't gain any information because your photons are automatically broken, because they can't all hit an area and create a pattern back out. And so this is why all these rules are connected. So it has to be a very one fact leads to another fact leads to another fact, and that's fine. And I'm all for somebody doing that someday, going through every single one of these elements. But you're expecting me to do that? I mean, you're expecting me to be an expert in every one of these fields, to sit there and tie up every single loose possible end, when you haven't demanded any of this from their theory. Their theory doesn't give you any of these details in any coherent manner whatsoever. But anyway, I don't mind doing it. I'm just saying it is a lot of detail. Alright, you said not random but 50-50. So the idea is that obviously the photons have a frequency going in, okay, a consistent one. And so all you're saying is when I scatter them at these different angles, there's a 50-50 chance it's going into phase or out of phase. So they can't be something else besides out of phase or in phase. There's no other option. So they're going to fit in one of those two categories, where they just happen to get more in phase or they just happen to get more out of phase. I'm saying the same amount of energy, the same number of little bits. The little bits come out of, see, these are just one simple fact. Like if you could just accept the one fact, we would be okay. The number of the bits are being scattered. They're not being scattered to a location. They're being scattered to all locations. So they're hitting every single place. They're hitting with the exact same amount of energy. There's no pattern. There's just a bunch of bullets hitting. So every square inch is getting hit with the same number of bullets. The difference is there are places where the bullets are in phase, and so, I mean, in the sense that you now have a path length difference that's a whole number, so now you have them back in the same sequence here. The bullet that left here and the bullet that left here will now restore the frequency. They have the same period between them. So this one will travel the longer path length and be this bullet, and this one will travel the shorter path length and be this bullet, right? So they'll be back in sequence. And so that's all you're saying, is that there's locations where the bullets will be in the right sequence and locations where they'll be in some frequency that isn't in phase, that doesn't have the right period, and therefore won't be a photon. There'll be energy, but it won't be a photon. Alright. I want to be extra sure in understanding if this is 50-50 is some outcome on the screen but not on the slits. The 50-50 is just saying it's sort of random, but obviously the pattern shows us that it's not 50-50. I mean, half the pattern isn't dark and half the pattern is light. Obviously the light bleeds into more space than the dark. So you could argue that the centers of the nodes are in a certain location, but the nodes themselves won't be in those locations, in the sense that there's a lot of bleeding. And you can explain that as being either variances on the atomic scale of your slit surface. It's not exactly 500 nanometers. We can't make things that exact. 1 nanometer of difference kind of thing, because an atom is 5 nanometers, 0.5. So we're already going to have a hard time telling the atoms where they have to be. And likewise, the frequency doesn't have to be perfect. 500 nanometers exactly between each one. It could be 499 and it could be 503. Anyway, you pointed out that some bits could and will go in different directions. They'll all go in all kinds of directions, and yes, the directions will be completely even over time. Not in terms of I would argue that when you hit the electron, it can only bend a certain amount. Okay, its momentum is going to be a certain amount, and so you can only get so much bending out of it. It's not going supersonic speeds, so you can't get a whole bunch of bending. You can only get a little bit of bending with each hit of an electron. Thus, they would cause the mutual phase transition, caused by the recombination of scattered bits of the photon. So I don't know exactly what that sentence is saying. I don't think I should have to keep explaining, phase. It's just a period. You're just shooting bullets. The bullets go everywhere. But the fact is when they went into the thing that's changing their direction, they were in phase. They were in alignment, the right period. So you can restore the alignment of the bullets. Maybe even backscatter takes place on the slit surfaces. Obviously, some of it will reflect, but the reflection is what? The electron goes this way, the electron goes back that way. Yes, you're recreating photons in the opposite direction in some sense. That is happening. Light goes back towards the source. You can see that in laser experiments, when they send the signal, and they put it through a beam splitter and all this crap, that actually when the thing goes dark, they can find the light signal is coming back at them. It's actually, light is being reflected. So you're lighting this screen when this screen is dark, and when this screen is light, you're darkening this screen. So that's a phenomenon already pretty well established in the 50s. So I wonder how all these scatter effects could average to the outcome predicted by the path length difference projection on a circle. The key point is that, yes, if you do some averaging, you're going to be much better off than trying to find the 1/1,000,000th of a degree change in these thing, because you have a very slight ellipse instead of a perfect circle. Anyway, I guess technically it's not an ellipse, right? Ellipses are lopsided on one side. It's a oblongoid or whatever. It's obviously elliptical on, the two sides match, but the two sides aren't it's a little thinner in the middle and a little fatter at the ends, but it's so little that it can't matter. I'm kind of expecting that at the end we have to deal with the statistical scatter effect, even though the geometry gives the outcome of the probabilities of the lamps. I don't know what that means either. It's just, like I said, there's a ton of points to make, but obviously you're not going to get the same pattern in the same places, so this isn't some perfect, oh, that's wet again. Well, I'll save that point for some other time. It's not like there's it's like even when they did the fish tank experiment, right? They shoot the pattern, so the two slits, and then they look at it in a fish tank with ink in it, right? So they can see these vector lines. Those vector lines are sort of a lie, right? Because you're really saying, I'm going to see a little piece of red paint, right? A little fleck of red dye. I'm going to see that little piece of matter, because I'm going to shoot a photon off of it. So I'm already doing a calculation where, are they in phase at the location of that fleck? So it's the location of that fleck that's going to give me a piece of light. But it doesn't mean that there's a light vector that is going that way. The fact is that I'm combining two vectors again to see the piece of red dye. I'm doing the experiment with each little piece of red dye in all these different locations. I'm saying, is that piece of dye a wavelengths different? Right? It could be 10 wavelengths, it could be 5. It doesn't matter. It has to just be whole wavelength of difference. So do I have the potential to recreate the frequency? And yes, the truth is, yes, I do. Okay, and the fact that it's red dye, again, I'm absorbing some of it. I'm, reflecting some colors, right? So, it gets kind of a little bit complicated. They're using red light, that's why red dye, to ensure it's a reflection. And so, you can't use what you're seeing, because what you're seeing is a composite, the same composite of the target. So there is no straight line to a location, and they're all on that straight line. Like every single one of those lines is equidistant, because it won't be, right? That's why we have fringes that are circles and they go out. That's Newton's rings. There's not a straight line. It'll be on, it'll be off, it'll be on, it'll be off, it'll be on, it'll be off. So the pattern is more of it's some other line. You can't really draw a line from the two surfaces and say these all become path length differences that have a whole wavelength, because there is no straight line that'll do that. You might have got that, you might have nodded. Anyway, all right, so I wonder how the scatter effects would average. Prediction by the path length difference projected on circle. I'm kind of expecting at the end that we have to deal with the statistical scatter effect, even though the geometry gives the outcome of the probabilities of the lamp. So I don't know what the hell that's. Whatever. I have a few questions related to the geometry of the slit pattern. Okay. Are the on-off patterns really equidistant when they are projected to a circle? They are, I would argue they're close enough that it doesn't matter, okay, for the sake of the argument. But I'd also say, maybe you care, I don't even care. I'm just saying that I know a length of arc has a certain number of nodes. Do I really care if this one's a little bigger than these up here? Now, it's okay if they are. I'm just saying, but why should I, is that going to change anything really? In the sense that I know the average location. I know there's going to be 15. Does it matter that the first one is, 6 nanometers bigger than the 10th one? The one this over here? This one's a tiny, tiny bit bigger than this one. Does that matter any? I don't think it really does. All right. I made a simulation with GeoGebra, whatever the fuck that is, with the help of Mathematica equation solver. So I'm not too sure, garbage in, garbage out. So I'm not too sure your equation is perfectly clean, in the sense of what two lines or what vectors it's actually comparing and all of that crap. But anyway, when I project path length differences divided by wavelength whole number phases, they have an equidistant pattern in the x-axis, but not on the screen. So I don't even know what x-axis would mean, but fine. You can see an example from this interactive blah blah blah. So I went to it, and it's not very interactive. It's kind of clunky actually, but it doesn't matter. So I changed it a little bit because I wanted more. So the little dots are really close together here, and they're getting further and further apart, and by a dramatic amount in this example. So I would argue that it can never be this dramatic. So in converting it to a drawing, you've either made a mistake, somewhere in the mathematics where they convert the big scale into a small scale, they've distorted that tiny difference, or there's something wrong in your fundamental mathematics, because there's no way. It's such a tiny ellipse. Again, we're talking about a millimeter over meters of distance. So this arc is 3 meters, let's say, or 4 meters, or 5 meters of arc, and the most the distance can be is the distance of the slit, so less than a millimeter. So it's a circle that's less than a millimeter wider in one dimension than it is in the other dimension. So that can be the only thing causing any distortion in the size of the nodes. So I guess I would argue, okay, that it couldn't possibly be this huge number of difference. The number has to be a tiny difference. The difference between me shaving a millimeter off of this chalk. That's the most the difference can be. Is a tiny difference, not a gigantic difference. But again, as long as we agree that this is a certain number of nodes from 0 to, or 90 degrees to 0 degrees, there's a certain number of nodes, which would be half, okay, of the number that fit in between the surfaces. And if we agree on that point, does it really matter what size we give them? I mean, I'm saying I'd be all for a very clinical description of exactly their size, but I'm just saying it just gets to whether which circle you're measuring. And is the circle the perfect circle from this middle point, or is the circle this point, and that circle? Or is it this point as the center and that circle? So I'm just saying that's where it gets a little complicated, because really the point I've tried to make is this middle point, the 1 millimeter going straight up is sort of a dead zone. It's not applicable to either side because it's not really L distance, so to speak. It can't be because the two lines are obviously not going perpendicular, they're not straight. So that obviously the point where they intersect has to be something less than L distance, or I mean more than, because it's not straight. I'm just saying you really have to think about it as just sections, 4/4 of a pie that you've pulled away from each other a little bit or something, and you've only pulled them away in this dimension. So you've taken a circle, cut it into 4 sections, just get rid of the bottom half because you don't need that. So what do you have? You have 2 sections that are a little bit further away from each other, a little wider this way and a little narrower this way. But it's a tiny amount. It's all like, I will attempt to think of some other way to explain it, but it's a little bit, there's a huge subtlety in how what you could do is just create another equation that compensates for the fact that the L value changes as you change the angle. So as you change the angle, L gets a tiny bit longer. And then you could say that would be a compensation for the change in the node size. I mean, I think the only way to fix it is to fix it with, that's the wrong comment, a fix, where you just, compensate for the fact that you can't establish a constant because it is a focus. The focus is moving. Alright, you can see the example. Okay, I have not figured out the radius of the circle dependent of the pattern yet. Well, that's the whole point, right? Is that where is the real center? And I guess I'm sort of arguing for the left side and for the right side. The centers are a little different. Alright, I think it should cause to increase the max phase count when the radius of the circle is increased. I'm just saying you can't change how many points will be constructive. It's the only part that matters. So the number of points where there can possibly be a full wavelength of difference between the two vectors, that number is stuck being exactly consistent with the number in between the surfaces. Once you establish that, it just can't matter much, the rest of this stuff. But anyway, I remember Stephen Bro had made a video trying to experiment with radio waves using equidistant spacing in the receiver end. Apparently he did a bunch of experiments I never got to see. He has some sort of filter that has a bunch of little slots in it. It was in his double slit video. I never saw him do an experiment with the slotted one, because that's sort of to my microwave argument, but anyway, maybe that is not the way to arrange them if the circle geometry of the screen is used. Well, the point is when he's doing those experiments, my argument is he's trying to filter out one of the sources. So by directional antenna, it doesn't mean that you point the antenna at another antenna. It's that you block the signal from the other antenna. The directionality doesn't mean you point something, right? The directionality means you exclude the other stuff. So you're only seeing the one source. You can't see if the whole argument is that the energy is getting to the location and that there is no interference. Well, you can't see that if you're allowing it to keep interfering. So you block it. The idea of the directional antenna, again, isn't to focus on the one you're trying to see. The idea of the antenna is to block the one that's interfering with what you're seeing. You want to block the radio signal that's sending the harassment, that's sending the noise. So to see the signal, you need to get rid of the noise signal. So the directionality isn't about pointing to the one you want to see. It's about blocking the one you don't want to interfere with what you're seeing. See, he doesn't get these subtle points that are just really important. But anyway, so I have just started to play with this geometry, take it as a draft of a draft. Math is a bit more complicated than the special relativity Lorentz gamma factor geometry. Like I said, I think you're trying to do something that's unnecessarily complex. But go ahead. Don't let me get in your way. Of course, there is nothing too fancy here. It seems that one can solve the phase points on the circle by simple Pythagorean theorem by first counting the whole number of parts of the wavelength in the path length difference. I think you can do it by just recognizing that there's only going to be a certain number of points on the, that can possibly be a full wavelength difference, and that they have to be correlate exactly to how big your base is. But I don't know how you could change that number. It has to be the same as the number of wavelengths that fit in the base. Those are the only triangles you can make out of the base. The base is what's going to give you the number of triangles you can possibly make, that will have a wavelength of difference, that'll have a path length difference that's a wavelength. And if you just draw the triangles, I don't see a problem. Anyway, and using those numbers to solve one rather simple equation, I have depicted blah blah blah. But eventually, one will have to sine, cosine, oscillating waves to have all of the algebraic equation. What do you think? I think it's really good to figure out explicitly, but I'm just saying maybe there's a way of modeling it, okay, that doesn't have to be explicitly a mathematical formulation. Now you can't just do this. Now I wish you could do just draw 2 points, draw a circle, and just say, I'll just use a ruler, okay? And I'll just see how long the ruler is here, and I'll take off what's on here, and every time I get an inch difference on the ruler, I'll just make a mark. Now apparently that's really not going to work, because this proportion has nothing to do with this proportion. So mechanically, I'm so far from the reality that I really have created a gigantic ellipse. This ellipse is like this. Okay, it's a really big ellipse. So there's going to be a huge difference between this and this. All right, well, it's only this here. So obviously, I'm going to get giant spacing differences. But I'm just saying, if you assume a circle, okay, then you can just say that there's really no ground for any difference, because there's no difference between 0 degrees and 90 degrees. It just doesn't, this could be 0 degrees and this could be 90 degrees. I can change this orientation to anything, and why would I think the notches could be a different size? They'd have to be the same size if it was a perfect circle. So if it's so close to being a perfect circle that it doesn't matter, why don't I just assume it? Why fiddle for this tiny little difference? I'm just saying, I'm not opposed to math. I'm just saying you have to be kind of careful. Math can fuck things up just as much as it can show you something. It can lie to you. So you have to know your math is rigorous. And I'm not a mathematician, so I can't really. No point in me commenting. That's why I evade math, is because I'm not an expert. And I can't be sure the formulas are correct. It's really important. If your formula's wrong, it's the whole MV squared thing. Wrong formula, you're going to get wrong answers. Once I got the on and offs right, I may turn to the double slit version of the simulation. So let's understand, this should be a fact you can agree with. The double slit version is nothing. It's meaningless. Okay. The difference is meaningless. It's such a tiny difference. What you're doing in the double slit is nothing. Okay, you're doing all single slit analysis, really. It's really just all single slit. And there's no part of this that you even need to. I'm being excessive in my rhetoric. I'll pause and see if I can drive this stupid thing. It's always something. All right, I'm back. Okay, so we'll deal with this, and we'll call it a day. All right, so you don't need any math special to the double slit, because as I'm asserting quite aggressively to you, is that the double slit is really just two single slit experiments. Okay, that's all it is, and it's not these two. Okay, it's this one and this one. All right. So you just do your figuring for what this will create. So these two surfaces, you figure what do these two surfaces do? What pattern do they create? You draw it. Okay, so obviously a small distance, it's going to make a big central maxima, and we'll have something like that. Alright, so that's the pattern you're going to get from these two. And then you figure out what's the pattern I'm going to get from these two. So it's all single slit math. So I just do this single slit experiment, figure out what pattern am I going to get. Alright, it'll come out to be something like, let's just put 6 of them in here. Okay, something like this, right? And now all you're going to do, alright, is just say, where do these overlap? Where do these overlap? Where do these overlap? Okay, and that's going to be where you have constructive. So where the four sources are both in the same phase, okay, so where the phase of this one is same, and the phase from these two is same, alright, and those two are the same phase, that's where you're going to have a spot. So I'm just saying that's how simple it is. So the two slit math would just be, once you have the geometry in a mathematical form of this pattern, you just combine the two in an XOR way. Okay, I mean in a, XOR, I think is the way you say that. I'm just saying where they match, it's an on. Where they don't match, it's an off. That's it. So this is an off. Okay, because it only has one contributor. This is an off because there's only one contributor. Okay, and in between here, it's only one contributor, right? There's one here, but there's not one here, so 0. And that's all. The end. Double slit solved. It's just two single slit experiments directly superimposed on each other, and you can understand it that way, or you could just understand that's what the four sources are going to do. When you brought these two slits into proximity to each other, you fundamentally changed their distances. This distance became a distance, and this distance. So this distance became a new distance introduced, and this distance changed. So, it's not just about this and this. That's the irrelevant part. The relevant part is this and this. Okay. I think that's let's see how much more we got here. Okay. By the way, let's see, another part, right, relative to the fact, depending on the slit width, most of the photons that would go straight through the lamp in the middle of the screen. Would you just add, depends on the background, how long you have played with the geometry. Even then, the simulator, it's always a good way to confirm results. Yeah, I'm all for a mathematical simulation, but I'd rather it was my math, I guess is the point. Seeing is believing, doing is even more convincing, usually offering interesting geometric, well, anyway, so that's fine. I mean, obviously my math has an assumption in it. The assumption is the nodes are the same size. But whatever. How would you calculate that precise? Let's see. Would you add the straightforward band almost the width of the slit to the screen? See, I should have read the whole thing. Another part of getting the center of the pattern right is related to the fact that depending on the slit width, most of the photons will go straight through the lamp to the middle of the screen. Would you just add a straightforward band almost the width of the slit to the screen. Yes. I mean, it's obviously going to spread a little bit just because of your imperfections, but I'm just saying what starts off as a millimeter really does have to end as a millimeter. It can't expand because it doesn't have any deflection. It hasn't been diverged. How would you calculate that precisely, and how does the intensity of the lamps on the screen differ? So the intensity is a whole nother subject, how bright, because that depends on what you're assuming to be how many photons or what the probability of deflection is. In their conventional theory, I don't think they have any clue at all. They just made it up. They just say, though, 93% of the light goes to the center, and then they say only 3% goes here, and then they cut it to 1.5%, and then they cut it to 0.75%. I don't think that's true. What is the variable that controls it? The experiments shown online videos look like the brightness is not linear, but based on some curvature. Whatever. Again, that's another detail to go through, but you really would have to do, you really need some nice evidence to analyze to figure out what the tendency is in terms of the intensity of the light. By the way, could you theoretically make a slit from certain material and stabilize electrons by some mechanism cooled to near 0 kelvins? Oh yeah, I remember this. I must have read this at some point. There's no such thing as 0 degrees. Okay, it's just kind of the bullshit. Because real degrees, see, the movement of atoms is what we're calling temperature. But what's really moving in the atoms is real temperature. So you're never going to get an electron to 0 degrees. An electron is sitting in the real universe and is getting hit by these photons all the time. You're not going to stop that from happening. You're not going to be able to get rid of the force. You're not going to be able to evacuate the force from a chamber. You're never going to create a vacuum of force. And so the electron is not stopping. What could prevent electrons from interacting with photons, or is absolute zero only freezing the protons? It's not even doing that. Absolute zero is not, it's just freezing atoms. It's freezing the motion of the entire solar system, but it's not freezing the motion inside of the system. This also reminds me of some comments that slit surfaces made of any material could cause the interference pattern. I guess this is a bit more complicated because what kind of material would we think is suitable for the surfaces after all? Well, again, this doesn't really have anything to do with transmitting light. It's just about surfaces, and all materials have to have a surface. All atoms have a surface. Electrons. So even if you did a single atom, technically you're going to scatter part of a photon with a single atom. You can't scatter the whole photon. You can't scatter more than one piece of the photon, but you still certainly can scatter some element of a photon with a single atom. All right. Anyway, funny exits in your commentary videos. They're probably they're not very humorous from this side of the camera, frankly. This whole thing has just been such a tedious, horrible experience. I just never, I had no expectation that people would be so resistant. Again, the simple argument I'm making is their physics sucks. The evidence sucks. The reasoning sucks. The logic sucks. I mean, bent space is logical mush. It doesn't, again, you can't make bent space work in 3 dimensions. It's not bent anymore. It's converging space. So they don't even have language that fits their actual theory. I mean, these theories are so bad. This physics is so freaking bad. And the fact that I can get no traction on that argument, that's the one that should just be, yes, people should be willing to say, you know what, yeah, that is all kind of just bullshitty. I mean, this whole wave particle duality, yeah, that's just bullshitty. I get it. That's bullshit. Many universes, all these silly, dark matter, this is silly shit. This is, there's no good reason to believe this stuff. These aren't well evidenced, facts. Not even close. I mean, the fact that, and then the fact that I have piled on a really very simple theory, but, nothing can be, I can't just do what Ken Wheeler did, right? I can't just say to you, well, look, the double slit experiment is this. There's one over here, and then there's one and one. There, that's a double slit experiment. Got it? I mean, I can't get away with that, right? I shouldn't get away with that. But regular physics is getting away with this. Ken Wheeler's getting away with this. And that's the irritating part. I can't get away with anything. I have to go into insane minutia detail. They don't even have to give you a rational outline. They don't even have to draw the rabbit anything like a rabbit. Where you're telling me, I have to tell you how long his claws are, what's the exact chemistry of his fur, how many ticks are sticking to him. It's just so unfair. But whatever. It's the way of the world. This is the world I have to fight in, so I will fight as best I can in the, by silly Martian rules. That's the rules. Okay, I'll play by Martian rules. Which appear to be, you throw a brick in the head and you measure how heavy it is by letting it hit you in the head. The rules seem pretty silly. But anyway, so till the next time and such. This has been a DraftScience video presentation. Thank you for your participation in this case. Thank you for participating in a reasonable manner. Much appreciated. And such. What am I supposed to do now?